We've talked about how computers find each other across the entire planet. But let's be honest, we don't really care if two machines can talk. We care if our programs can talk, if we can connect. That's where the real magic happens, and it all takes place in two absolutely critical layers we're about to explore, the transport and application layers.
I mean, really think about it. On your computer right now, you might have a web browser open, an email client running, maybe a game, and they're all using the internet at the same time. So when a new email arrives, how does it know to go to your email app and not, say, your online game? How does that web page get delivered to your browser and not your spreadsheet? This is the central puzzle we're going to solve today.
So, here's our roadmap. First, we'll visit what I like to call the Internet's post office, the transport layer. Then, we'll eavesdrop on the very polite and structured conversation that programs have using TCP. From there, we'll jump up to the application layer to see how they all learn to speak the same language. We'll also meet the digital gatekeepers, firewalls, and finally, we'll put it all together and trace a single web request from the moment you click to the moment the page loads.
All right, let's get right into it. The transport layer. Its main job is to be the ultimate traffic director, a super efficient sorting office that makes sure every single piece of data gets delivered to the exact application it was intended for. To manage all this potential chaos, the transport layer has two key jobs with fancy names: multiplexing and demultiplexing. But it's actually pretty simple. Multiplexing is like an on-ramp to the highway. It takes all the data from your different apps and merges it into one single stream. And demultiplexing? Well, that's the off-ramp. It takes that incoming stream of data and sorts it all out, directing each piece to the correct program. The big question, though, is how does it know which off-ramp to take? The secret is something called a port. A port is just a 16-bit number, which means we have about 65,000 of them to play with. Each port acts as a unique digital doorway for a specific service. So, for example, regular web traffic almost always knocks on the door of port 80, while a secure file transfer will use a totally different one.
And this analogy just nails the concept perfectly. An IP address gets the data to the right building, the correct computer. But the port number, that's the specific apartment number. It tells the delivery person exactly which door to leave the package at. Without the port, all your data would just get dumped in the lobby.
Now, here's where it gets really cool. The transport layer actually gives us a choice between two different kinds of delivery services, TCP and UDP. TCP is like sending a package with tracking and requiring a signature. It's meticulous. It establishes a connection, it makes sure every single piece arrives in order, and it asks for confirmation. It's all about reliability, which is why your web pages and emails depend on it. UDP, on the other hand, is like sending a postcard. You just write it and drop it in the mail. It's incredibly fast and efficient, but there's no guarantee it'll get there. This is perfect for video streaming or online gaming, where speed is everything, and losing a tiny bit of data isn't a disaster. It's always this fundamental trade-off. Do you need perfect reliability, or do you need raw speed?
Since so much of what we do online absolutely depends on that reliability, let's zoom in on TCP. The way it manages connections is pretty amazing. It's like a very formal, very polite conversation using special signals to manage the entire exchange. These signals are called control flags, and they're the basic vocabulary of the conversation. The four most important ones are SYN, which is basically saying, "Hello, I'd like to start a conversation." Then there's ACK, which means "I heard you." You've got FIN for "Okay, I'm finished talking now." And finally, RST, which is the emergency abort mission button if something goes wrong.
So every single TCP connection kicks off with what we call the three-way handshake. It's this beautiful little dance. First, your computer sends a SYN packet saying, "Hey, can we talk?" The server on the other end replies with a SYN and ACK packet, which means, "Yes, we can talk and I acknowledge your request." Then, your computer sends one last ACK packet saying, "Great, I acknowledge your acknowledgement." And boom, just like that, the connection is established and data can start to flow.
Ending the conversation is just as polite and orderly. It's a four-way handshake. One computer sends a FIN flag saying, "I'm done sending data." The other computer sends back an ACK to say, "Roger that, I heard you." Then, when the second computer is also ready to close up shop, it sends its own FIN flag. The first computer sends one final ACK, and the connection is gracefully terminated. No loose ends. Okay, so we have our port, our apartment number. But how does a program actually listen at that door? Well, it uses something called a socket. Here's the difference. A port is just the number on the door. A socket is the program actually opening the door and actively listening for a knock.
It turns a static address into a live, active endpoint. And a socket isn't just on or off. It goes through a whole life cycle, and these states tell the story of that life. A server will have a socket in the listen state, just waiting. When your computer initiates that handshake, its socket enters the SYN_sent state. Once everything is connected, both are in the established state. This is where the real action happens. And as they start to close down, they'll go through FIN-wait states until finally they're closed. For anyone who has to troubleshoot networks, these states are like clues at a crime scene. They tell you exactly where the conversation broke down.
Okay, let's climb one step higher. Once the transport layer has built us this nice, reliable connection, the applications themselves need to be able to understand each other. And that is the whole job of the application layer. Now, here's the crucial thing. The application layer isn't one single language. It's more like a massive library of different languages, or as we call them, protocols. There's a protocol for web browsing, another one for email, another for file transfers. Each protocol is a universal rulebook for a specific task, making sure that any two programs designed for that task can talk, no matter who wrote them.
Web traffic is the absolute perfect example of this in action. You have tons of different web browsers, Chrome, Firefox, Safari, and on the other side, lots of different web servers like Apache or Nginx. They can all communicate flawlessly with each other for one reason. They all agree to speak the same application layer protocol, HTTP. That standardization is literally what makes the World Wide Web possible.
So now we have all these programs chatting with each other through thousands of these little port doorways. That sounds like it could get a little chaotic, maybe even insecure. And that brings us to the role of the firewall, our network's digital gatekeeper.
A firewall, at its heart, is a pretty simple idea. It's just a program or a dedicated device that inspects all the traffic coming and going. Its job is to decide, based on a set of rules, whether to let that traffic pass or to block it. It is the primary line of defense for almost any network.
And while firewalls can get very sophisticated, their most common and powerful job happens right here at the transport layer. Why? Because of those port numbers. A firewall acts like a security guard for our apartment building. We can give it a simple rule. Only allow deliveries to apartment 80, our web server. Turn away anyone trying to get to any other apartment. It's a simple concept, but it's the foundation of modern network security.
Okay, we've covered all the individual pieces. We've seen the layers, the protocols, the ports. Now let's put it all together and watch how they all work in perfect harmony to handle something we do 1,000 times a day: clicking on a link. And this whole symphony happens in milliseconds. First, your browser opens a socket, getting ready to talk. Then the transport layer does that three-way handshake, SYN, SYN-ACK, ACK, to build a reliable TCP connection to the web server's port 80. Once that connection is established, the application layer sends an HTTP request through it. Along the journey, a firewall inspects the request, sees it's headed for the approved port 80, and lets it pass. The server gets it, sends the web page data back. And finally, once the page is loaded, the four-way handshake politely closes the connection to free up resources. Every layer, every protocol working in perfect concert.
It's just incredible when you stop and think about it. Every single click you make triggers this complex, polite, high-speed conversation that can span the entire globe. It's the invisible architecture holding our entire digital world together. So the next time a page is loading slowly, don't just see a delay. See a conversation that might have broken down. Which part of the handshake failed? Is a firewall blocking the port? Suddenly, you're not just a user anymore. You're a detective, and that changes how you see the internet forever.